Hi everyone. So we'll get started now. So just before we begin, my name's Clodagh and I'm from DIAS. I work in Dublin Institute for Advanced Studies, or DIAS, and we run this lecture series, Samhain Agus Science, every year. This is our last talk for this year, but if you're interested in seeing any of the previous talks, I'll leave a link to our YouTube channel in the chat. So this talk is Are We Living in the Anthropocene by Professor Mark Williams. And just to tell you a little bit about Mark before we begin, he's a professor of paleobiology in University of Leicester. He's worked in the British Geological and British Antarctic surveys as a scientist, and he's worked for over a decade on Anthropocene research, and he's a longtime member of the Anthropocene Working Group. So during this talk, if you've got any questions, please leave them in the Q&A and we'll have a look at them at the end. And I think that's nearly all of our attendees now. So well, I'll hand you over to Mark now for the talk.
Thank you, Clodagh. I'll just try to share my screen. So hopefully everybody can see my screen now. If somebody could just confirm that. Can you see my screen? Can you hear me?
Yeah, we can see you and hear you.
Okay, that's great. So thank you very much for that introduction, Clodagh, and thank you very much for coming this evening. What I'd like to chat to you about over the next 50 minutes or so is the idea that humans have become such immense agents of geological change that we have left the Holocene epoch of geological time, and we now live in a new epoch of geological time called the Anthropocene, which is denoted by our actions as immense agents at the surface of this planet. And really, I've kind of subdivided this talk into 4 different areas because I think we should actually start by asking the question, just how special is the Earth, the place that we all live? And then I'm going to ask how we've changed the Earth and what is actually driving this change. And then if I can get you to agree that the changes are so immense that we should define a geological epoch called the Anthropocene, then I'll show you how we might go about doing that. And at the very end, I just want to ask a philosophical question, really, about why it might be useful to think about an Anthropocene epoch of geological time. So I'm going to begin by asking the question, how special is the Earth? And it's a special place, of course. It's sustained a biosphere for about 4 billion years. And it may well therefore be a biological jewel in the cosmos. For all we know, it is the only place in the cosmos where there is life. But certainly the complexity of life on planet Earth is something to really treasure. And yet you could argue that the past kind of 600 years of science have in some ways actually changed our notions of our special place in the cosmos, because if, of course, we went to a pre-Copernican view of the cosmos, we would think of the Earth at the center of creation, at the center of the universe. But science, of course, has shown that that's not the case, that we are a small terrestrial planet orbiting a rather common type of star. And indeed, you know, there have been many estimates for our Milky Way, for our galaxy, that suggest that there may be many millions of stars in the habitable zone in our galaxy, and that perhaps 500,000 stars in our own galaxy might have Earth-like biospheres. These are at least some of the suggestions that have been made, which might make us think that actually, well, maybe we're not so special in the universe. I'm going to argue very much for the opposite as I go through this talk. And I just want to point out that even though the SETI program, the Search for Extraterrestrial Intelligence, has been going for about 60 years, it hasn't identified any convincing extraterrestrials out there so far. And that might actually make us think that we're a bit more special than we sometimes think. I rather like this image of the pale blue dot. It's the image taken by the Voyager 1 spacecraft as it left our solar system on February the 14th, 1990. And that image of us is taken from 6 billion kilometers away in deep space. It was an image requested by the famous astrophysicist Carl Sagan, and it really says it all. I mean, that is our cosmic oasis. That is the place where we live, where everyone we've ever known has lived, and where everyone we'll ever know probably is going to live. It's a very, very special place, an oasis drifting in the desert of space. Now, even if we could go boldly in our spaceships, and we may try to do this, I guess, in the not too distant future, there isn't really anywhere that we can boldly go that is remotely like planet Earth in the near vicinity of the Earth. Our two sister planets, Venus here, is a very inhospitable place for life. The surface of the planet, of course, would probably crush you from the atmospheric pressure. And if the atmospheric pressure didn't get you, then the surface temperature of over 400 degrees Celsius would almost certainly do for you. So likely not a very hospitable place, at least for life at the surface of Venus. And our other close neighbor, Mars, often touted as a place where there may be life. Well, there may be life on Mars, of course, but it's not going to be the kind of complex biosphere that's evolved on planet Earth for 4 billion years. Indeed, it doesn't really look like the most hospitable place, does it? It's a desert, and we can't even breathe the atmosphere there. And I think the irony of some of the ideas that we've developed in the late 20th and early 21st century, the idea, for example, of colonizing Mars and of building biomes there, biomes, of course, which would have to conserve absolutely everything, recycle, regenerate as a way of sustaining life at the surface. When we think about that, there's a real irony, because here on this wonderful planet that we live on, we do the exact opposite. We don't conserve, we trash, and we trash at an alarming rate. And I'm going to give you some of the statistics of that trashing a little bit later as we go through this talk. And I just also want to point out that, you know, the Earth is obviously a wonderful place to sustain life, and it has been one for billions of years. But the components of the Earth system that actually sustain life at its surface are really finite. I think this is a wonderful image by the artist Adam Neiman, and it's really gathering up all the water at the surface of planet Earth and the atmosphere at the surface of planet Earth. And it shows you, when they're gathered up into these balls, just how finite those life support systems are at the surface of our planet. In fact, you know, a comparison is that the hydrosphere at the surface of our planet is thinner than the skin of an apple in a relative sense. Okay, it's a very special place where we live, and it has a complex biosphere that's co-evolved with other components of the Earth system, perhaps for 4 billion years. We need to ask the question then, how are things changing at present that make me as a geologist think that we should be thinking about defining a new epoch of geological time? I think it's fairly evident, if you're passing on the dark side of planet Earth, for example, that something very substantial has happened here over the past couple of centuries in particular, because the night sky now is obviously ablaze with the lights of hundreds of cities with more than 1 million people, and many of those cities with more than 10 million people. Of course, there are now 8 billion of us on this planet, and that's increasing by around about 80 million every year. So adding the population of a country like Germany each year to global population. We live in vast structures. We live in large megacities, you know, sometimes 10 million, sometimes 20 million, in a few cases, 30 million or more. And these cities in general are growing as time goes on. And I just want to contrast that, because there are 8 billion of us, with the numbers of our closest relatives. How many do they number relative to the 8 billion humans on planet Earth? Let's just have a look at our two closest relatives. So our two closest relatives are the chimpanzee, with a global population of around about 250,000, and then the beautiful bonobos, with a population of about 20,000. So our two closest relatives number one small human city and one human town in their total populations. And the staggering figure here, I think, is that you and I, as Homo sapiens, are about 99.9% of the numerical abundance of all primates at the surface of this planet, which is a remarkable, if depressing, figure for any single species, any large single species to have achieved. We dominate the biosphere like no other primate, like no other species. We've been reconfiguring the biosphere. We have estimates perhaps of 1 million species at risk of extinction, but of course we haven't quantified the number of species that exist on our planet yet. So these are estimates. It could be much more. We've halved the mass of the biosphere. Because most of the mass of the biosphere is in forests, on land, we can calculate the relative loss of this over the past 10 millennia. And it seems that you and I as a species have actually halved the biosphere's mass. We've concentrated mass in domesticated animals and in ourselves. You and I and the animals that we like to consume are about 95% of the terrestrial mammal biomass. So all wild mammal biomass is less than 5% compared to us and our commensal animals. Again, a staggering figure for one species to control biomass in this way. And you can see that if you look at global maps, for example, of farming. Half the habitable land of planet Earth is used for farming. 3/4 of this is used for animals and dairy. And about 1/3 of the land under crops is also used to feed our farm animals. So systematic reconfiguration of the landscape and its ecosystems. And we've profoundly changed the organisms within those ecosystems. So this is what we've done to chickens over the past 60 years or so, because we like eating them. We've increased their individual mass fourfold. We eat 63 billion of them every year, and there are about 21.5 billion specimens of chicken on the planet at any one time, an order of magnitude greater than the next most populous bird, which is numbers about 1.5 billion in the wild. We move Earth, and we don't just move a small amount of Earth, we move an order of magnitude more Earth than all of the rivers on planet Earth. About 316 gigatons of sediments is produced by humans each year. So we are definitely gigantic geological agents at the surface of the planet. We use about 4,000 cubic kilometers of fresh water every year. I have real problems in actually visualizing what that means, but if you think of a large lake, Lake Malawi in Africa, for example, that's the equivalent of humanity draining that lake every 2 years for its consumption. We use vast amounts of energy, and that energy consumption has been accelerating as a result of population growth. This is showing primary energy resources, but we could add to that the energy that we extract from the biosphere, and then we really are approaching gigantic sums of energy that we consume as a species. We changed the atmosphere too, of course. In 2021, we put another 38 billion tons of carbon dioxide into the atmosphere, with its clear impacts on global climate and oceanography. And uniquely for any species in Earth history, we don't just dominate the land, we also dominate the sea. We take vast amounts of fishery products from the oceans each year, which has resulted in fishing down the food web in the oceans. But of course, we're also planning to extract large amounts of mineral deposits from the oceans too, which will have an equally damaging impact on ocean ecosystems, potentially. Well, I don't want to linger too long on the figures because they're all overwhelming, but I am going to come back to some of this granularity a little later, because I do at this point need to introduce an idea to you of one of the notions that is driving all of this change, and the fact that it's not just humans, but it's also the technosphere. Now, the technosphere might be a new term to you. It's the brainchild of Peter Haff at Duke University in the USA. Peter is part of the Anthropocene working group that I'm also a part of. And Peter has defined this thus. So the technosphere is the autonomous global system that drives the Anthropocene. And note the word autonomous global system, that it means it's out of our effective control. It comprises the world's humans, its technological systems, transportation, communication, power, financial networks, governments, bureaucracies, military, educational establishments, religious institutions, all manner of political and artistic organizations also. It's an emergent system. It is a complex system that is growing out of the biosphere and it is growing out of humanity. But you and I as individuals, nation states even, humanity as a whole, now has relatively limited control over the direction of travel of the technosphere. It has its own autonomy, as Peter would strongly argue. It's vast. It's a sphere like the other spheres of the Earth system, the hydrosphere or the atmosphere or the biosphere. And it's overcoming the ability of other spheres to meet its demands for raw materials. And that's because it hasn't co-evolved with those other components of the Earth system. The biosphere, the atmosphere, of course, and the lithosphere and the hydrosphere have co-evolved over billions of years, but the technosphere is a rapidly, newly emerging system. The problem for us is that we cannot exist without it. We couldn't be having this conversation now without the technosphere. And indeed, it is the technosphere that is sustaining 8 billion of us on this planet. If it were to disappear tomorrow, it would be impossible to sustain all of those people. And it's vast. A few years back, we tried to add up the total weight of the technosphere. More recent study has actually suggested that the technosphere now weighs more than the biosphere. So this is a massive structure that is everywhere at the surface of the planet, both in the oceans and on the land. Peter Haff would argue that this is an accelerating process, and that eventually, if we're not able to train the technosphere to operate in a more mutually beneficial way with the other components of the Earth system, that the wheels will fall off. I'll come back to the technosphere a little bit later. I want to park it for a while because I want you to think about the technosphere, but I also want to ask the question, how did we get here? How did we get to a state where humanity and its technosphere are now driving the major changes at the surface of the planet Earth? And how might we, as geologists or scientists, actually define the Anthropocene? I want to show you what the physical record of geological impacts from humans is, particularly with relation to the fossil record, because I am a paleontologist by training. So, of course, one of the great contributions of geology to science is the development of this geological timescale. It's a way of understanding the complexity of how the Earth system has evolved over more than 4 billion years. I mean, you can see from the right-hand side up to the top left that basically time is getting younger from more than 4 billion years ago, right the way through to the Holocene, top left, yellow there in the Cenozoic, which is the epoch of geological time that we are currently within. We haven't formally defined the Anthropocene yet. Now, all of these boundaries that you can see on this geological timescale are important. They represent quite fundamental changes in the Earth system. And those fundamental changes we use to subdivide geological time to give us a framework to understand the way in which this Earth system has evolved over this enormity of time. And to do that with our framework, we need events that are effectively isochronous, that are of equivalent age everywhere on the planet. It's that framework which then allows us to understand the processes that may have led to those major events. So synchroneity in our events, when we define geological boundaries like this, is of paramount importance. Now, thinking about that and thinking about the geological timescale, we, for the Anthropocene, therefore need an event which is effectively traceable in deposits everywhere, which designates an isochronous surface. Just as we would define the boundary between the Cretaceous and the Paleogene, it's 66 million years ago at the time of impact of this major asteroid in the Gulf of Mexico. We need an equivalent kind of, not necessarily an equivalent event, because we don't want an asteroid strike at the surface of planet Earth, but we need an event that allows us synchroneity to give us our framework on which we can then organize all of the processes of humanity, or reorganizing the Earth system over millennia and millions of years. So we're looking for that synchroneity when we try to define our geological boundary. So how are we going to find that boundary? And obviously we'd like to try and define a boundary also which is synchronous with when humans really come to dominate the Earth system. How might we go about looking for that? Some of the processes that we have to think about examining in terms of trying to define this Anthropocene geological boundary are processes which have unfolded on planet Earth from humanity over hundreds of thousands or indeed millions of years. We have to think about our impact from hunting and gathering, which begins nearly 3 million years ago and which is still playing out in some landscapes today. We also need to think about landscape domestication, how we've changed the Earth as a result of agriculture. And also we can think about globalization, processes where transportation systems and human cultures have become interconnected, particularly over the past 500 years. And I'm going to examine each of these in turn to see if any of them might potentially provide a geological boundary for the Anthropocene. So do any of these leave a record that might characterize the Anthropocene? And remember, we're looking for this synchroneity of signal as well as potential magnitude. Let's begin with hunting and gathering then. Humans as a species, or as a group of species, originated about 2.8 million years ago. And there's certainly evidence for hunting and gathering, which gathers pace in the paleontological record from around about 50,000 years ago. A more contentious, but nevertheless possible evidence of human impacts on the landscape much earlier than this, going back in some cases in Africa more than 1 million years. So let's look at the paleontological signal of hunting and gathering to see how it might be important in terms of thinking about human impacts on the planet and thinking about the Anthropocene. So the earliest records of humanity are really our tools, and in fact tool use or tool manufacture goes back prior to our group of species. It's older than the genus Homo. It goes back to our sister primates, the Australopithecines, more than 3 million years ago. We as a group of species start to leave evidence of our fossil record in the rock successions of Africa from about 2.8 million years ago. And from about 300,000 years ago in North Africa, we start to indicate records of anatomically modern humans. So Homo sapiens that were structurally very similar, anatomically very similar to us. From around about 70,000 years ago, and that accelerates really beyond those millennia, we start to show signs of modern behavior. So this is cave art from about 40,000 years ago, extending from Europe to Indonesia, and indicating that Homo sapiens at this time are beginning to think in ways and means in the way that modern humans do, that they are not just anatomically modern, but that effectively they're becoming culturally modern also. Now, this is important because around about the time that we start to see evidence for culturally modern humans, we also start to see the impacts of humanity on the broader biosphere and Earth system. It's around about this time, from about 50,000 years ago, that we can connect the disappearance of certain animals from the landscape. This is the time when the megafauna, large mammals of 44 kilograms or more, start to disappear from different ecosystems around the planet as humanity extends into those different regions. So ground sleuths, for example, ground slopes disappear from the Americas a few thousand years after humans arrive. Now, it's possible that some of these megafauna extinctions of these large mammals and also large birds are also caused by climate change during this interval of the late Pleistocene and going into the Holocene. But it seems likely from recent studies that much of the impact is from humans. And it's also very clear that in those regions where humans had not co-evolved with these megafaunal animals, in places like the Americas and in Australasia, that the impact of humans on these animals was much greater. And this is manifested as a very clear paleontological signal that we can find from the Americas to Australia. So it's a global paleontological signal of human impacts on the planet. Now, this is obviously important in terms of changing ecosystems globally, but it's not something that I can use as a geologist to define a geological boundary. And that's because it's not synchronous. It doesn't show me a signal that's of equivalent age in the Americas to that in Australia. We see the megafauna extinctions beginning about 50,000 years ago in Australia, when modern humans get there. We don't really see this appearing in the American landscape until about 13 to 12,000 years ago. So there's no synchronicity here. So this doesn't work from a geologist's perspective in terms of defining a geological boundary. But nevertheless, it's very important in terms of our unfolding impact on the Earth system. What about landscape domestication then? Can I use that to define the Anthropocene? Is it the big event that's synchronous that I can trace across the planet to define the boundary between what went before and the Anthropocene now? Well, landscape domestication is generally thought of beginning around about 13,000 years ago in the Near East, in places like the Levant. Although, in fact, there is evidence that people were already trying to trial cultivate wild cereals, perhaps as early as 23,000 years ago. Just like all of these human impacts on the planet, this is a process that unfolds over a long period of time. It's also a process that evolves in different places using different crops and therefore giving different paleontological signals according to whether you're in the Americas, where maize might be a good marker of this change, or whether you're in the Middle East, where wheat might be a good marker, or whether you're in the Far East, where rice might give you a key signal. Now, all of these have left a clear paleontological signal of pollen and also archaeological signal of the plants themselves. But again, despite the fact that this is a fundamental change caused by humans, it doesn't give me that synchronative signal that I need as a geologist to define a geological boundary. So these developments, just like the megafauna extinction, are strongly time transgressive, and time transgressive there simply means occurring at different times in different places. They were also subject to the whims of climate and environmental change, and so in some cases were actually reversed, and therefore I can't use them to define a geological boundary for the Anthropocene. What about the third major process that I've talked about then with relation to humans? And what about globalization? And here I'm going to take an relatively arbitrary boundary of 1500 CE as the time of the Columbian exchange, though noting that there was very strong interconnectedness between humans via the Silk Road, for example, or by trans-Indian Ocean trade a long time before this. So this is also a part of a process which unfolds over thousands of years, but which has certainly accelerated since the Columbian exchange joined the Americas with what was called the Old World, around about 1500 CE. What about globalization then? Well, we could look at the spread of crops like maize around planet Earth, and the spread of maize has also left a distinctive paleontological signal of its pollen where it's being cultivated. Maize, of course, was first cultivated perhaps 9,000 years ago in Mesoamerica. It gradually spread through the Americas, and then it much more rapidly spread around the world after the Columbian exchange, as you can see here in this figure put together by my colleague Colin Waters. And that's left a distinctive paleontological signal in lakes in Africa, for example, where I can find maize pollen from about the early 18th century onwards. Or I could think about tobacco pollen. You can find tobacco pollen, obviously again, tobacco sourced in the Americas. Pollen occurs in 17th century clay pipes from Rembrandt's house in Amsterdam. These are clay pipes which have been recovered from the old loo in Rembrandt's house. Again, they give a clear indication of the Columbian exchange, but rather like the spread of maize pollen around the world, this is not a signal which is going to help me define a synchronous boundary, the big event that allows me to understand time of equivalent time everywhere at the surface of planet Earth, which is essential for geologists. So none of the early Columbian exchange signals of globalization can be widely documented from the sedimentary record, and none of them provide that isochronous, that time synchronicity that I need as a geologist to establish my framework in order to understand processes of geological change at the surface of planet Earth, and which my science as a geologist demands that I do. However, as we go on through the process of globalization, these processes begin to accelerate as we go forward in time from the 15th, 16th, 17th, 18th, 19th, and 20th century. These processes will accelerate. Agriculture, for example, will develop to feed billions of us. And many of us will mass in huge cities. And in order to get people to move around those huge cities, we'll have to build gigantic trace fossils of our activity. Many animal species have burrowed in the geological record, and they've left a fossil record of that. But no species has burrowed in the way that humans burrow. So here, the London Metro being formed in 1861, it's an order of magnitude greater in size and complexity than anything that we'd find in the non-human component of the geological record. But nevertheless, these are burrows, these are trace fossils of human activity. These trace fossils have extended across planet Earth over the past 150 years, and now pretty much all ice-free continents have a record of these metro systems, which will be a global and probably permanent signal of human activity at the near surface of planet Earth that will last for millions of years into the future. So the next time you travel in a metro system, just remember that you're traveling in a human burrow, a human trace fossil that will be preserved long into the future. Now, all of these signals that I've explored with you are of profound importance for cultural and human evolution and for our technological achievements. But none of these earlier signals can be used by me as a geologist to define a geological boundary. They're all time transgressive. Just like the metro systems, they've developed over a period of 150 years. They don't give me the precision that I need to define a geological boundary. particularly in the context of where we are dealing with historical time. For geology, I need an event that is essentially simultaneous and can be traced in deposits everywhere. And I need this because geologists have to deal with the enormous complexity of 4.5 billion years of Earth history. And in order to understand processes of change, we have to have a framework of time that enables us to understand time, equivalent time, in different places on the planet. That's really the only way that we can start to assemble data sets of deep time that allow us to understand how the planet's evolved. For example, if you were trying to model a deep time climate that might be similar to warm climates of the near future, you'd need to be absolutely certain that the data that you were building into your data set, perhaps some 3 million years ago, was of equivalent time everywhere. And that's the crucial nature of defining these isochronous surfaces in deep time. But I would argue, and the other members of the Anthropocene working group would argue, that an isochronous signature can now be found on planet Earth in the way in which humans change the Earth system now. In the most recent stages of globalization, in the middle to later part of the 20th century, and I'm going to show you how that works. It works because we have global signals that we can use, that we can recognize in lots of different sedimentary successions around the world that give us this high precision synchronicity. So we can find radioactive signals of plutonium and cesium and americium that are related to the detonations of atomic bombs in the middle part of the 20th century, which, if you like, are our event horizon, rather like the asteroid strike at the Cretaceous Paleogene boundary 66 million years ago. So the radiogenic signals give us this isochronicity, and it's that isochronicity which also dovetails in the middle part of the 20th century with a whole range of other parameters that show profound changes to the Earth system during this interval of time. So if you remember that everywhere we go, we can find in sedimentary successions plutonium, americium, cesium as indicators of these atomic bomb blasts, and that gives us a very precise marker for the middle part of the 20th century. That also dovetails with a whole series of other changes. It dovetails with biogeographical changes in the morphology of cities. So top left, I'm showing you an Anglo-Saxon church from near to where I live in Northamptonshire in England. And bottom left, I'm showing you a Hindu temple from Vietnam, from southern Vietnam. Top right, I'm showing you the city of London. And bottom right, I'm showing you the city of Ho Chi Minh City. Now, the two images on the left would clearly give you a biogeographical indication of Anglo-Saxon England and of medieval Vietnam. But the two images on the right are almost interchangeable. London and Ho Chi Minh City are built from the same materials, from glass, plastic, concrete, steel, materials that are globally traded, commodities that now form the blood, if you like, the engine of the technosphere. And this international style of architecture becomes very much the fore in the middle to late part of the 20th century. It's not just this, of course. It dovetails with a whole series of other changes that we might style as part of Will Stephan, another member of the Anthropocene Working Group from the Australian National University. The Great Acceleration, this time in the post-Second World War period when a whole series of different parameters changed very dramatically. You can see some of them here, things like damming of rivers, fertilization, fertilizer consumption, international tourism, and even the spread of McDonald's restaurants in the latter part of the 20th and 21st century. There are now 38,000 McDonald's restaurants at the surface of planet Earth. All of these have also left clear geological signatures. So here I'm just giving you some of the examples of the kinds of geological signatures that we see, that we can record in the various cores that we've been looking at around the planet. And I'm going to give you a bit of the granularity of some of those studies shortly in a few minutes. But you can see that this mid-20th century period of time shows very, very significant changes in the Earth system as a result of the accelerating patterns of consumption of humanity and its technosphere. The 500 billion tons of concrete and 8 billion tons of plastic produced since 1950 alone, which have left a clear geological signature in the sedimentary record. So it's evident that the scale of change is massive in the 20th century, and I've shown you a few examples, but there are many other examples I could also show you. How does this actually preserve in the geological record? How can I demonstrate to you that human impacts can not only be quantified in terms of what we can observe going on around us, but that the geological record itself is now preserving the dramatic changes that humans have produced at the surface of the planet? So here I need to talk a little bit more about the work of the Anthropocene Working Group that I've been a part of now for 14 years. These are the different sites on planet Earth that we've been looking at over the past 6 years to try and see if we can recognize this major change in the Earth system in the mid-20th century in the geological record. And you can see that we've looked at lots of different places. So we have Pacific reefs, we have an ice core from Palmerland on the Antarctic Peninsula, a Chinese lake, a Japanese bay. In Europe, we have the Baltic Sea, a Polish peat bog, an Italian cave, and the city of Vienna itself. And in the Americas, we have a Canadian lake, we have a reef in the Gulf of Mexico, and we have San Francisco Bay and Searsville Reservoir in the hinterland of San Francisco Bay in California. Now, I can't take you to all of these different sites because I don't have time to do it, but I'm going to take you to one. I'm going to show you the profound impact of humanity on planet Earth, clearly recorded in sedimentary records from San Francisco Bay. So we're going to go to the California coast now. We're going to look at one of these Anthropocene successions in high detail. So here we are in San Francisco Bay. Something very significant has changed. Indeed, the bay ecosystems are now fundamentally reconfigured. There is very little left of the ecosystems that occurred here, even before Europeans first arrived in the 19th century. The indigenous people that had lived in this region for millennia had actually lived in a very sympathetic way with the biosphere here for thousands of years, but everything has dramatically changed since the California gold rush of the 1850s. We can see clear evidence of that in the physical record, and we can also see clear evidence of San Francisco Bay and San Francisco and Oakland as being major seaports, as part of one of these major nodes of the technosphere and its transportation of materials around the planet. So it might be transporting steel or cars or concrete or what have you, but also as a product of this transportation of materials, the technosphere is also inadvertently, or in some cases deliberately, transferred many species around planet Earth to reconfigure global ecosystems. And actually, I use this as a snapshot of the global marine transport networks. At any time, you can go to this website, you can watch this unfolding at present. And it really is quite amazing, if not dramatic, to just visually watch the number of ships that are moving about on the oceans at any one time. And it is therefore inevitable that this has produced an homogenization of the biosphere, as many organisms have hitched lifts on these boats within their ballast waters, for example, or on the hulls themselves. Let me just show you how this is unfolded, for example, in San Francisco Bay. So here we're coring in San Francisco Bay. This is a project with one of my former PhD students, Stephen Himpson, working with the United States Geological Survey to try and gauge what the physical paleontological record of these changes in San Francisco Bay might be. Do we have a paleontological record, for example, that we can compare with changes in deep time? So there in the inset figure, you can see lots of the different cores that we've taken, and overall we've examined about 20 different cores from San Francisco Bay. So a pretty good data set. Why San Francisco Bay? Well, this graph is plotting for you the non-native species that have arrived in San Francisco Bay since the California gold rush in the middle part of the 19th century. And those figures on the right-hand side are really quite striking and are worth, I think, just flagging to you. 234 introduced species recorded in the bay since 1850. Half of all those introductions have happened in the last 35 years or so. So this is very much an accelerating process. And that bottom one, I think, is really quite frightening in some ways. Non-native organisms in San Francisco Bay can account for 97% of the total number of organisms and 99% of the biomass in some parts of San Francisco Bay. So we really are talking about a wholly reconfigured ecosystem here, particularly so occurring in the later part of the 20th century. So let's just have a look at some of these introduced species into San Francisco Bay. The Manila clam arrives in 1946, and of course the Manila clam is not native to San Francisco Bay, it's native to the waters around the Philippines. When it arrives, it's like many introduced species into San Francisco Bay, it proliferates. Here you have a picture of the Manila clam in some places, forming dense patches of clams of more than 2,000 individuals per square meter. And of course, when organisms proliferate like this, they often leave very little space for the indigenous species. So this is not good from the perspective of the local ecosystems. Manila clams are just one of many of these introduced species that we can find in San Francisco Bay. And some of these non-natives we can recognize as being very widespread markers in our cores. So we have our cores across San Francisco Bay. We can work through those cores. We can produce age models of the timing of when those cores, when the sediments were forming. And we can recognize the incomings of these different species from their fossil records within these cores. So here you've got some of the introduced species into San Francisco Bay, which have left a fossil record in these cores. On the left-hand side here, you've got microfossils. So A to B are ostracods. These are tiny crustaceans, so relatives and crabs and lobsters, but only a millimeter long and enclosed within a bivalved carapace. At the bottom, C to D, bottom D2 and D3, you have foraminifera. A foraminifera called Trocomina haydai, which is also now found widespread in our cores. All of these taxa that you can see here originated in East Asia. So again, they've been introduced into San Francisco Bay by shipping. And on the right, you have the Amur River clam. So that's a mollusk. It's a macrofossil. Again, we get it in our cores, and it originated in East Asia. The Amur River gives it away because the Amur River is a boundary, forms a boundary between China and Russia. So all of these are invaders from East Asia that have been transported on ships across the Pacific. And just like the Manila clam, they proliferate. So here I'm going to show you what's happened with Amur River clams. You can see they arrived in San Francisco Bay in 1986. That's when they were documented. It rapidly became the most abundant seabed organism in the Northern Bay. By 1988, they reached average population densities of 2,000 individuals per meter squared. And that kind of proliferation of this species meant that it actually reconfigured the entire ecosystem. Its arrival caused the summer diatom bloom to disappear because these organisms were actually filtering. They were eating all of the phytoplankton in the bay, and that had a significant impact on food webs. And what you can see at the top there is that by the early 1990s, in some places, there were nearly 20,000 individuals of these Amur River clams per meter squared in some parts of San Francisco Bay. So a very significant change to ecosystems and a very clear paleontological signal of this. This is the foraminifera Trocomina haydai. It arrives from Japan in 1983. It also has proliferated across the bay. It's now replaced the indigenous most abundant species, which was Elphidium excavatum. And you can see in many places, Trocomina haydai is now by far the most abundant benthic foraminifera. So foraminifera are single-celled organisms that produce a very distinctive shell that you can see there preserved bottom left. Trocomina haydai, this invasive species, is now the most abundant foraminifera in many places on the seabed of San Francisco Bay. Now, this is a complicated figure, but it's one being produced by my PhD student, Stephen Himpson. And what it's basically showing you here is in all of the different cores, so these are numbered from 21A across to 106 on the right, from left to right-hand side here. Wherever we look in the bay, in the upper part of the sedimentary succession, we find these wholly reconfigured ecosystems. And what Stephen is trying to do here with all of these different tie lines is just to show that this reconfigured ecosystem can be traced across the whole bay. that not only is this something that we can observe in the actual physical record about us, but this is also preserving as a distinctive paleontological signal in San Francisco Bay that will be preserved into the future. Now that's interesting in itself, but it's only showing you one region of planet Earth. If I'm going to start trying to compare these paleontological signals with deep time signals, then we should be able to replicate these kind of faunal turnovers in lots of different places on planet Earth. So now let's travel 4,000 kilometers across the Pacific Ocean. Let's go to a very remote site. We'll go to certainly remote geographically, although connected obviously by the technosphere. Let's go to Hawaii, or the Hawaiian Islands. This is also a place on planet Earth where many non-native species have been introduced. You can see there the number of invasive species is very striking in the Hawaiian Islands, and it's having a major impact on the ecosystems there. This is a process which has unfolded for 1,000 years, with Polynesian people being the first to import organisms into these islands, things like the Pacific rat, for example. But it's a process which has accelerated very dramatically into the 20th century with European interference. The introduction of things like the giant African snail, there at the top and bottom right, the cannibal snail has also been introduced into the Hawaiian Islands. And it's left a very distinctive paleontological signal. So here we are on the island of Kauai in the Hawaiian Islands. And on the left-hand side here, you've got a stratigraphical record, a sedimentary record from one of the sinkholes on this island. You can see that sinkhole bottom right there. And in that sinkhole sedimentary record, there is a fossil record of the snails that have lived on Kauai for hundreds of years, thousands of years in some cases. And what I hope you can see is that the indigenous snails at the bottom there have now been completely replaced by the introduction of the cannibal snail and the giant African snail. So the indigenous snails are now extinct, and they've been replaced by these introduced snails that leave a signal, a fossil signal from the middle part of the 20th century, enabling me as a geologist to use paleontology to correlate over thousands of kilometers to that 20th century, that mid to late 20th century interval. Well, the point I'm trying to make to you here is that these patterns come to resemble those that we see in deep time geological successions with, from the middle part of the 20th century, extinction and replacement of assemblages by these changes in fauna and flora globally, which signifies this massive acceleration of human impacts at the surface of the planet in the middle to later part of the 20th century, leaving a very distinctive paleontological signal of human impacts. So what I've tried to do so far is to talk about how special planet Earth is, to think about why we might go about defining an Anthropocene epoch, looking at the degree of change that humans have enacted at the surface of the planet, and then demonstrating to you with a high degree of granularity in one succession in San Francisco Bay, but I could do this in any of those successions I showed you that the Anthropocene Working Group has been looking at, that this has left a very clear signal in the geological record, which is effectively permanent. The final part of this talk really is a philosophical question to all of you about why we might actually think it's important to define the Anthropocene. One could argue that we have historical accounts of the changes that have been enacted by humans over thousands of years, and that we can clearly see that accelerating process in the 20th century. So why not just think about this from a historical perspective, or indeed from an archaeological perspective? Why might it be important from a geological perspective also to think about these processes? Well, I want to start that brief philosophical discussion by just reminding you about the technosphere, and also reminding you that much of the consumption in the technosphere is driven by cities, and that processes of urbanization at the surface of planet Earth are accelerating, so that more and more people will be living in cities in the coming decades. And of course, that will be tied in tandem with a growing human population, at least into the middle part of the 21st century. So we might expect the technosphere to become even more greedy in its consumption of the Earth system as a result of this. I'm often struck by the description of metropolis in Fritz Lang's film, but I just want to point out to you that Tokyo covers an area 3 times the size that metropolis is assumed to have covered. So already these processes of urban development are accelerating beyond what we thought in the past. And the patterns of consumption of cities, and indeed of the broader impact of humans and the technosphere on our planet, resemble a parasitic relationship with the rest of the biosphere. We are consuming without returning materials that will sustain the biosphere in its longer term. And that's entirely counterproductive to what's happened with the evolution of the biosphere over billions of years. Many of our solutions to this actually seem to involve more consumption. So instead of actually thinking about the ways in which we might consume less, we actually transfer our patterns of consumption to using different kinds of materials that will still have a very considerable impact on the Earth system. No matter how far we kid ourselves that using electric vehicles, for example, will solve the problem, it most definitely will not. So rather than looking for solutions that can reduce consumption, in fact, we look for other patterns of consumption. Peter Haff would argue that this is the technosphere actually trying to accelerate its impacts on the planet. We also prefer to think that our cities of the future will be greener, but just exactly what do we feel by that or mean by that? This looks like a green city, but look closer. The buildings don't look as though they can regrow or be reused, so nothing like the structures that are produced by the biosphere. The air conditioners are a giveaway that this is not a sustainable city, and of course the growth in the production of air conditioners is very rapid in some parts of the world and is a very strong positive feedback mechanism, making climate even warmer. And the traffic on the nearby highway, top right, that you might have noticed is another clear indication that this is not a green, sustainable city long into the future. Well, we talk about smart cities as being very efficient, and indeed they can be, and certainly this is part of some of the mechanisms that we might use to solve some of our broader problems with the Earth system. We also talk about sustainable cities, which are good at managing growth. But neither may be a long-term solution to human consumption, and that's because neither of them are trying to emulate patterns of natural ecosystems that are very good at recycling and regenerating. This is why I think it is very important that we need to remind ourselves that we are massive geological agents at the surface of planet Earth. And this is why I think it's so important for us to contextualize the Anthropocene also as humans as major geological forces. Now we are so major, in fact, that we are beginning to approach that asteroid strike at the Cretaceous-Paleogene boundary in terms of the damage that we can do to the broader Earth system. And that should remind us that if we and the biosphere are to thrive, the solutions need to be much more radical in the way in which we as a species interact with the rest of the Earth system and with the biosphere. The biosphere, of course, has sustained itself for billions of years because it's predicated mostly on the primary energy of the sun. It engineers interrelationships between organisms that foster biodiversity. It conserves and recycles the things it needs to survive, things that the technosphere is not doing very well at the moment. So we need structures that replicate this too. We need cities that seek to emulate natural ecosystems that have co-evolved with the available mineral, biological, water, and energy resources of their environment. And that is going to mean very radical changes to the way in which we structure our cities and the way in which they interact with the landscapes around them. Of course, there are no such cities on planet Earth at present, but a few cities are trying to go in this direction. Well worth having a look at what Burlington in Vermont is trying to do. It's in the vanguard of trying to be much more mutualistic with the environment around it. Some civilizations in the past have been remarkably good at sustainability. I'm not suggesting that Tokugawa Japan is a panacea in terms of the way it treated some people within that society, but it was remarkably good at recycling materials to sustain itself over a long period of time when Japan was closed off from the outside world. Indeed, during this period, Japan developed industries that recycled pottery, that recycled metalwork, that were very good in reusing human waste, for example. And now, of course, many of the artifacts and materials that were repaired, broken pottery, for example, in Japanese culture are treasured items. Repaired broken pottery is a treasured item. Maybe that's something that we should be thinking about more as we talk about regeneration of planet Earth and the ecosystems that we want to build in the future. Now, if we can slow the pace of consumption, that might buy us some time with the technosphere, and that might enable us to train the technosphere to have a successful relationship with the biosphere going forwards, just in the manner that the other components of the Earth system have been able to develop a mutually beneficial relationship which has preserved a habitable space at the surface of planet Earth. And indeed, that might help us to stop the wheels falling off the technosphere, using the parlance of Peter Haff. I'm coming to the end of my talk now, but I just want to start with a geologist's kind of prediction of the two likely outcomes of the near future. And of course, it's always difficult to be trying to predict where we might go, but I think these two are very strong possibilities. And geology is very good actually at giving us hindsight to what might be the near future also. Human changes to the Earth system might become short-lived and unsustainable. They may be marked with an Anthropocene mass extinction, which of course is a very good geological marker for me because it will leave a distinctive paleontological signal, but it's very bad for the Earth system and it's very bad for humanity going forward. What I've tried to suggest at the very end of this talk is that although that we're in a process of an accelerating process of technospheric consumption at planet Earth, we do understand how the technosphere is working, and we may be able to modify its behavior so it becomes much more mutualistic with its relationship between the Earth system and its human technospheric components. That is, we want to evolve a technosphere that becomes sustainable over the long time frame, over geological time frames, and can co-evolve in a beneficial manner with the rest of the Earth system. Now, that's obviously a good outcome for the Earth system. It's a good outcome for us and the biosphere. But even in that scenario, if that is going to be the future, I would proffer to you that humanity and the technosphere have changed the Earth system so substantially. It is so radically different from anything that has occurred in Earth history in the past that we are unequivocally in a new epoch of geological time. That new epoch is the Anthropocene, and the best place to mark the geological boundary would be in the middle part of the 20th century with those radiogenic isotope signals that give us a synchronous signature that correlates with these massive changes to the Earth system that we can find from the 20th century onwards. Thank you very much for listening to me, and obviously very happy to answer any questions at the end of this. Gone very quiet out there.
If there's any questions, the Q&A is open there if anyone wants to put any questions in.
One of the things I wanted to pose to you was, the fact that SETI has been looking for civilizations in the cosmos for 60 years or so. And it's very quiet out there. Of course, it's quite possible that other civilizations have evolved, and those civilizations must also have evolved technospheres if they became as complicated and sophisticated as the human technosphere has become. I hope that isn't telling us something more broadly about the longevity of civilizations when they evolve technospheres, and I'd be really interested to think what your views on that might be.
I think we've got a question, one question here from Rachel. I'll just pull it up here. So Rachel's asking, I was interested in the claims in San Francisco Bay. It seems like they behave just like humans taking over. Are we really all that unique?
So it's a good question. So I guess we're not unique in the sense that invasive species often can have a very dramatic impact on the ecosystems that they invade. But actually many of what I didn't have a chance to talk about is the fact that many introduced species can be quite benign, and sometimes they can be quite beneficial to ecosystems too. So it's not all black, but it is very important in terms of thinking about the broader change to the global ecosystems, where diversity, global biodiversity, is clearly declining at a very rapid rate. And yes, many invasive species do behave in exactly the same way that humans do, in doing damage to the ecosystems around them. But of course, we have been the vectors of those introduced species. So we're responsible for most of those introductions. And we've been doing it for probably 20,000 years. But the process has accelerated very dramatically in the later part of the 20th century as a result of this globalization of humanity.
Thanks. And we've got one more question here from Greg. Have you heard of Kate Raworth's donut economics, which argues that a new economics must not exceed certain environmental boundaries? Would something like that help us to survive?
Yes, so I know Kate Raworth's work, and it's very good, and I know donut economics, and I think she's also been applying a lot of her ideas and models to urban contexts, also in the redesign of urban ecosystems, and absolutely I applaud that kind of approach. And she's absolutely right, as many other kind of urban ecologists have pointed out. If we carry on at the rates of consumption that we have at present, and if our urban designs continue to operate as parasites and don't develop mutualistic relationships with the rest of the biosphere, then the result of that is inevitable. So we have to go in that direction very rapidly, and many cities are trying to do that. But for me, and I'm sure for you also, I am very frustrated at the pace of change. I mean, we're talking about changes that need to happen in a very rapid succession now. One of the things we don't have is much time. But yes, Kate Raworth's work, absolutely brilliant. So I like that a lot.
And maybe just one more question before we finish. From Betty, there are some people saying that we shouldn't define an epoch while we're in it. Are those voices being heard? And could we just define this as an event for now?
So there's been a very strong discussion in the geological literature over the past few months about thinking about an event versus defining a geological boundary. There are many events in geological time, but they've actually been fairly poorly defined. And we've just written a research paper which has actually tried to put a much more precise definition on events. The problem with events is that they're often defined as major episodes of geological change. So the Great Oxygenation Event, for example, occurred between about 2.5 billion years ago and 2.2 billion years ago, unfolded over 300 million years. And of course, it's that time when oxygenic photosynthesis evolved and fundamentally changed the biosphere. But of course, that's a very long process of change, just as the human impact on planet Earth has also unfolded over millions of years. Now, for me as a geologist to be able to understand how those events relate in space in time, I need that framework. If I don't have that framework of equivalent time that I can then hang on all of these other changes, it becomes very complex to understand those different processes. So you could argue that we don't need that from an historical perspective, but I've tried to argue that I think it's very important that we do. And of course, because I'm a geologist, I have to follow the strictures of the way in which my science defines geological boundaries. And that's why I'm looking for this synchronous event. And others obviously are looking for this synchronous event. And we can see that in the 20th century.
Okay, I think we should probably wrap it up there. Thank you so much for joining us and for an amazing talk. And also thank you to everyone who joined here as a participant. And I hope you really enjoyed it. There's a link there in the chat for our other Samhain Agus science lectures. And this lecture will be on the YouTube channel as well once it's up. So once again, I'd just like to say thank you to Mark for an amazing talk. And thanks for taking time out of the evening to come here and talk to us.
Thank you very much for inviting me. Nice to chat with everybody.
Yep.
Okay, bye-bye.